Okay, so for this problem, a rectangular box is to be made so that the top and bottom are squares, and the volume is 250 cubic centimeters. So let me draw a picture of that, like a brown box. So the top and the bottom are squares, but we don't know what the height of the box will be. Okay, so if the top and the bottom are squares, that means that the length and the width of the box are going to be the same dimension, so I'll call them X. And then I'm going to call the height of the box Y. Okay, and we know that the volume, which volume, remember, is length times width times height for a rectangular prism, that's going to be 250 cubic centimeters. And since the length is X, the width is X, and the height is Y, 250 will be equal to X squared times Y. Material for the top and bottom costs $2 per square centimeter, but the material for the sides costs $1 per square centimeter. What dimensions will minimize the cost of materials? So it sounds like we are trying to minimize the cost, meaning we need to have an equation that represents the cost. So this volume equation is actually going to end up being our secondary equation. Okay, so the total cost will be the cost of the bottom plus the cost of the top plus the cost of each side. So since the top and the bottom both cost $2 per square centimeter, let's just focus in on the bottom. To determine the cost of just the bottom, I would do $2 times whatever the area of the bottom is. The area of the bottom would be represented as X squared. So the cost of the bottom would be 2X squared. The cost of the top would also be 2X squared. And the cost of one of the sides, so let's say just the cost of this side right here, would be $1 times the area of that side. Well, the area of that side would be XY. So that would be $1 times XY. And then there's 4 of those sides. So plus XY plus XY plus XY. So if we simplify that, our cost equation would be 4X squared plus 4XY. And we can't take the derivative yet. This is our optimization equation. But we can't take the derivative yet. We need to use our secondary equation in order to rewrite our cost equation in terms of a single variable. So why don't we solve for y in our secondary equation? So I'm going to come over here. If I solve for y is equal to 250 divided by x squared. So now I can come back to my optimization equation. I'll still have 4x squared plus 4x, and then I'm replacing y with 250 divided by x squared. And I want to simplify that before I actually take the derivative. So this x is going to cancel with one of the x's in the denominator. 4 times 250 is 1,000. So I would have 4x squared plus 1,000 over x is equal to the cost. And then to make taking the derivative a little bit easier, I'm going to rewrite that as 4x squared plus 1000 times x to the negative first so that I can just use power rule. So now we're ready to take the derivative of our optimization equation so that we can find the critical values. So C prime will be 8x minus 1000 times x to the negative second. Rewriting that without the negative exponents. And then remember, to find the critical values, we're looking for where the derivative is equal to 0 and where it's undefined. So to make that easier, we want to rewrite our derivative as a single fraction so that we're just setting the numerator equal to 0 and then setting the denominator equal to 0. This first term can be thought of as 8x over 1. So I'm going to multiply the 8x by x squared over x squared, leaving me with 8x cubed minus 1000 all over x squared. It's up to you. If you want to write the C prime for each step, you can, or you can just have those equal signs showing that they're equal to the previous step. Okay, if we were to set the denominator equal to 0 and solve, it's easy to see by inspection that 0 would make the denominator 0. We need to come back up to our optimization equation to check what our domain is for our cost equation. Now, x represents the length and the width. And we can't have negative length and width. X could technically be 0, but if we look at our cost equation, where cost is a function of what the value of x is, right? Cost is dependent on what the length and width are. We see that x is in the denominator here. So if x were equal to 0, that would make our cost equation undefined. So we're going to define our cost equation, our optimization equation, for x strictly greater than 0, meaning an open interval. So in interval notation, that would be from 0 to positive infinity. 0 is not in the domain of our cost equation, meaning 0 cannot be a critical value. So now let's set our numerator equal to 0, and we'll solve for x. So if we add 1000 and then divide by 8, we get x cubed equals to 125. And then the cube root of 125 is 5. Okay, so 5 is on the interval for x strictly greater than 0, meaning that x will be our critical value. And because our optimization equation is defined on an open interval, this is where we'll use our analysis line and the first derivative test. I'm going to put my critical value on the analysis line, and I'm also going to put 0 over here as an endpoint of the interval. Okay, 0 is not included in the domain, but that's just reminding me that I need to choose a value that's between 0 and 5. So like I could use 1 as a test value, and then how about 6? And I'm plugging those test values into C prime. So when I plug 1 in, I would have 8 times 1 cubed minus 1000 all over 1 squared. And we can see that would definitely give us a negative value. That would give us negative 992. So from between 0 and 5, the graph of our cost equation is going to be decreasing. And then when we plug or substitute 6 in for x into our derivative, let's see. we get 182 over 9. So the graph will switch to be increasing. So on the interval from 0 to positive infinity, where our cost equation is defined, the graph would end up going from decreasing to and change to increasing when x is equal to 5, making x equal to 5 the location of the absolute minimum for our cost equation on that interval. So this, remember I told you guys that you just need to, this is enough work. Now you can write your sentence. Let's double check what the question is asking for. And these are multiple choice, so you don't technically have to write a sentence for them, but if you were making your screencast, you would want to write a sentence. So it says, what dimensions will minimize the cost of the materials? Well, we know the length and the width are going to be 5 centimeters. So it looks like A is going to be our answer here. So Jackie was in the gym. And then we could find what the height would be by coming back up to this equation where y is already solved for. So if we were to do y equals to 250 divided by 5 squared, right, that would give us 10. So the height of the box that would minimize the cost would be 10 centimeters. So to minimize the cost of the box, the box must be 5 centimeters by 5 centimeters by 10 centimeters, or some variation of that.